Alright, so let's look at this final example where I need to find the intersection and angle between these two planes. Now, with these two planes, I only have two equations, but I have three variables. So I have a unique math challenge here to find a whole system of solutions that work, because a single coordinate will come out of this because the intersection of two planes would make a line, right? Like your two hands run together, your two planes run together, and it makes a line of intersection. So I'm expecting the equation of a line to come out of this. First, I'll start over here in the margin because this is a bigger problem. I need some space. X minus 2y plus 3z is also 1. And so just like my system of equations solving skills, I'm going to subtract these, and I'll come out with 3y minus 2z is 0. And I would get something like 3y equals 2z, or y equals 2/3 z. Now, I'll go and plug that back in so I can get what x is in this problem. X plus 2/3 z plus z is 1. X plus 5/3 z is 1. X is 1 minus 5/3 z. And our equation of a line, as we learned on the previous page, needs to be determined on t. X, y, and z all need to be dependent upon t, time. Well, here, it's dependent on z, So what I'm going to do is I'm going to choose that z is t. Because then x is 1 minus 5/3 t, y is 2/3 t, and all of a sudden I have an equation of a line. Can you see it? In this case, my x is 1 minus 5/3 t, my y is 2/3 t, my z is just t. Like if you wanted to look at it in terms of that coordinate plus change vector, I'd have 1 for my x, 0 for my y, and 0 for my z. But my t values would be negative 5/3, 2/3, and 1. But I don't really love these fractions, so I could even use a scalar multiple, a parallel fraction, or a parallel vector to this one. So I could also do something like this, and it would still be the tangent line. Both of these would be acceptable solutions. I could even turn them into symmetric equations if I cared to. And now to find the angle of intersection between these two planes, well, I have a normal here, 1, 1, 1. I have a normal here, 1, negative 2, 3. And so I'm just finding the angle between these two normals, right? I have a vector and a vector. I find the angle between two vectors using the dot product. And I just run through those calculations. When I dot these, I get 2. For a magnitude, I get 3. For a magnitude, I get 13. I use my inverse cosine function. Where if I plug that into a calculator, I get a cool 71.32 degrees. It's tricky, it can be difficult, but what you have to realize is that these x's depend on t, these y's depend on t, these z's depend on t, so I can even substitute those in for each other. I'm not going to get too far into it, but you have to be comfortable kind of going between these worlds, between the vector form, from the normal, and from the coordinate to a line, to a plane. You have to see how points, lines, and planes interact in the 3 space in this lesson.